for the invitation. So this will be the talk about how to compute S metrics for a process where you do have both electrically charged particle and magnetically charged particle. Okay, so this is the based on the work on these two papers I listed here. And in the first paper, we really developed a formalism which allows us to compute this electromagnetic S matrix, which I call. And in the second paper, we study a little bit more carefully general multi-particle state. But I will mention some of the fact that I will use from the second paper. But anyway, so let's get started. And this is based on the collaboration with this group of people. All right. And before I start, I should mention that you should interrupt me and then jump in and ask questions whenever something is not clear. Okay. And as Professor Pyongwon mentioned, I thought that it may be important and crucial to include some amount of review part because our work is basically first part of our work is generalization of the existing spinor helicity formalisms. So I thought, unless audience already are very familiar with the existing formalisms, I thought it may be good to include some review of those stuff, which I will do. And then I will explain how we can generalize that formalism in case where we do have both electrically and magnetically charged particles. Okay. And then in the second part, I will go on to some application of the formalism and get some funs and physics, learn some physics about it. All right, so let's get started. So what is the motivation? So let me just give a few short word of the motivations. Okay, so let's say that somehow we live in a universe where we do have both electrically and magnetically charged particles. Okay, this is the line one assumption. Then we have learned from important works that Lagrange description of the simultaneous presence of both electrically and magnetically charged particles are very challenging. For example, Dirac argued that if we want to have a Lagrange description of both electrically and magnetically charged particle, you have to have some sort of known locality, okay, in the description. And this is often called as a mutually non-local. I mean, obviously, if our theory contains only electrically charged particle, we definitely know how to get the Lagrange description, which is a manifestly local. And same is true if the theory contains only magnetically charged particle. It is trivially local, it's good. But the problem is that if we want to bring both guys into the game, then all of a sudden there's this challenge. Alternatively, you can try to insist on locality. So let's say I'm gonna write down whatever. I'm gonna write down local description, but then Zwanziger showed that in that case, you need to introduce some sort of auxiliary vector, which basically encodes Dirac string, and therefore somehow you lose manifest Lorentz invariance. And this secretly encodes the fact that you also lose manifest gauge invariance as well. So it looks like it's very hard to maintain both locality and Lorentz invariance, and if you will, gauge invariance too. So then the question is, what's going on? What are we talking about, right? But in one recent paper by John Turning and Chris Verlaine, they managed to demonstrate that if you read some carefully soft photon exchanges, still you can restore manifest Lorentz and gauge invariance. Okay, but anyway, so my point here is that Lagrange description seems to be pretty challenging. Okay, but nonetheless, it is so obvious as to this question. Okay, let's say we are living in a universe with both electrically charged particle, which I call F for fermion, and magnetically charged particle, which I call M, capital M for the monopole. But somehow it should be so obvious that I should throw in both particles together and smash together and see what happens. So it's very natural to ask whether the scattering process does make sense at all. Okay. In other words, first of all, does this scattering process conceptually make sense at all? Meaning, I just talked about the fact that there's a challenge with maintaining both locality and Lorentz invariance. So the first question we can ask is that would this process actually local and Lorentz invariant? Okay. Now, if it turns out that it is actually a local and Lorentz invariant process and gauge invariance, as usual, you can put it in, then the second question is that how do we ever compute this S matrix? Okay, and let's say we manage to compute it. What kind of physics can we learn from this process? Okay, so the goal of today's talk is basically to argue that yes, it is manifestly local and Lorentz invariance, and I will prove this by just actually constructing manifested local unitary Lorentz invariant S matrix. I will use a formalism which allows me to construct a local Lorentz invariant unitary S matrix, and then I will talk about some non-trivial, pretty non-trivial aspect of physics of these scattering processes. Okay, so that's a basic motivation and the goal of the talk. Okay. By the way, I should say that this process is not perturbative. Okay, it's not like I have f in my theory. I mean, we do, but I'm not going to compute this process using tree-level factorization techniques. So we know that, for example, in theories where we do have two Polyakov monopole, those configuration is intrinsically non-perturbative. So it's not only that we have this issue with the locality Lorentz invariance, but what we are trying to do here is can I use modern scattering amplitude technique to even compute the process like this, which is governed by intrinsically non-perturbative physics? Okay, so I should just mention that. All right, so let's move on with that. So here is the outline of my talk. In the first part of my talk, I will talk a little bit about the multi-particle representation of Poincare group. In fact, the conventional wisdom is not very precise, and I will mention in what sense it is not precise, and then I will provide corrections to that. And then next, I will introduce what we call pairwise spinel helicity variables, which will be needed as an extra building block to construct the electric magnetic S matrix. And then in the next part, I will talk about the rules and building blocks, entire building blocks of the electromagnetic S matrix. And then I will use those rules and building blocks to construct some of the 3-point electromagnetic S matrices. Already, I will talk about some of the selection rules in this part. And then I will use this 3-point electric magnetic S matrix as a technique to perform fully relativistic version of the partial wave decomposition. And then I will mention very quickly unitary that I need to use. And using all these combinations of knowledges and techniques, then I will apply that to 2-to-2 scattering, like Fermion monopole scattering. And in particular, I will show that in its lowest partial wave, meaning with the smallest possible total angular momentum, the process is necessarily helicity flip. What that means is that if you throw in left, like a negative helicity fermion towards the monopole, what comes out at its lowest partial wave is opposite helicity state. Okay, you're not going to get, for example, by throwing negative helicity fermion into the monopole, you're not going to get the same helicity fermion out of it. Okay, this is already very non-trivial, weird thing about the monopole process. And then if I get some time, I will also talk about the higher partial wave processes or S metrics. And in fact, I will argue that full angular dependence can be completely fixed and determined once a little bit of a dynamical input is embedded or used. Okay, so that's the sort of brief outline of my talk. It's kind of long, but you see that there's a lot of ingredient before I can actually talk about physics. I mean, these are all physics, but I necessarily need to discuss how to build up electromagnetic S matrix first. So this part will include some amount of review, and you should feel free to interrupt me and ask questions whenever you get confused. Okay. Any questions before I move on? Okay, so if I don't hear in 3 seconds, I will just accept that as a no. But again, you should feel free to interrupt and ask me questions. All right, so let's talk about a little bit about the multi-particle representation of Poincare group. Okay, here I'm giving you super quick review for, first of all, one particle representation. Okay, so I'm interested in representation of the Poincare group for a particle with a momentum p. Okay, and then I'm going to be boosting that guy to a reference frame, which I call K. So this is the boost that brings a standard momentum K to, say, original momentum of the particle P. For massive particle, as I wrote here, for massive particle, I can go into the rest frame, and as I will show momentarily, and there is a group transformation that leaves this K invariant, and that is, as you see from here, SU2 transformation. For massless particle, on the other hand, you cannot go into the rest frame, but you can go into already this frame. And in this case, the little group, or the transformation that leaves this standard momentum invariant is U1, and that is the helicity part. Okay, once we understand this part, the quantum state, which I call this, which is a vector in the Hilbert space, is defined in such a way that, first of all, it diagonalizes momentum generators or translations, as I show here. So it's already momentum eigenstate. Then we can define a quantum state as this. So first of all, I have a quantum state in Hilbert space, which is determined in terms of standard momenta. And then the extra label sigma is basically spin or internal degrees of freedom. And then my particle state, one particle state is defined via this relation. This is basically a unitary operator that realizes a Lorentz boost. Okay, so this is the definition. Then you can study how this particle state transform under some Lorentz transformation, U. Okay, this is again unitary representation of the Lorentz transformation lambda. Without going through each steps, the final answer is this. Okay, so now you first of all try to do the Lorentz rotation for momenta. So it better be linear combination of the state whose momentum is lambda p. Okay, and then the sum over sigma prime is basically saying it's a linear combination. But then representation tells me that the precise linear combination is nothing but what's called the Wigner rotation. But I should say that this Wigner rotation is nothing but a rotation or transformation that leaves a k invariant. In other words, under arbitrary Lorentz transformation, one particle state transforms under a little group transformation. Again, little group transformation is what leaves the standard momentum invariant. Therefore, representation of the arbitrary one particle state is completely realized or characterized by the little group, not the Lorentz transformation. Okay, so one particle state is therefore little group tensor, not a little group vector, if you wish, not a Lorentz vector. Okay, I stressed that several times. It is a little group that characterizes full representation. Okay, this is the one particle. Then conventionally, we construct a multi-particle state as just a product of each one particle state. And representation of this guy is completely fixed once we understand the representation of each of these guys, because it's a tensor product. Okay, so we just talked about the fact that one particle state under arbitrary Lorentz transformation transforms under just little group rotation or Wigner rotation. Okay, and therefore multi-particle state transform under Lorentz transformation as a product of individual one particle Wigner rotations. Okay, so this is of course a very well-known study, well-known facts, for example from Weinberg chapter 2. Okay, so moving on. However, in this paper we argue that the general multi-particle state is not just this product state. Okay, remember product state is characterized by momentum of each particle and the spin of each particle. However, we show that the general multi-particle state has extra quantum numbers, which we call the pairwise helicity. So what is this? So let's just take the two particle state for as an example. But this can be easily generalized to arbitrary number of particles. Okay, so let's consider two particle state. Then I take the momentum of each of the particle and they go into a frame which using the simultaneous boost, the same boost, into a frame which I call the center of momentum frame. Okay, so basically one particle goes to the z direction, the other particle goes to the minus z direction. You can do that by using the boost. You can always go into this frame, even if it is a massless particle. Now, where PC and then EC, I just wrote the expression, which is not very important, but other than the fact it's a completely Lorentz invariant. Okay, so in this pairwise standard momenta, you see that in this frame there is a little group, meaning that leaves a pair invariant, which is obviously U1 transformation. Okay, so this argument, which is not completely rigorous, although we gave another construction which is more rigorous, is that the general two particle state, and therefore any number of particle state, has extra this U1 little group transformation on top of regular little group transformation of each individual particles. Okay, so therefore the point here is that maybe this is the best. If I take general two particle state, in addition to the usual momentum and spin of the individual particles, there is a pairwise, which is characterized by the momentum of the both particles. Okay, And so under arbitrary Lorentz transformation, in addition to the usual Wigner rotations of individual particles, it picks up the extra U1 phase factor, and whose phase depends on the momentum of the both particle, and whose quantum number we call a pairwise helicity. Okay, and therefore, if you have a multi-particle state with arbitrary number of particles, for each pair, you will have associated pairwise helicity. In fact,
Excuse me.
yes,
Excuse me. Could you go to the previous slide?
yes,
So here in the K, this you are talking about W12 and the K1, K2 in the center of momentum frame,
yes.
and the K1 and the K2 has a opposite direction.
Yeah,
Momentum.
oh yeah, I already gave you yours.
Oh yeah, yeah.
Yes.
The
Oh,
previous
yeah.
day.
I'm sorry. It should be my
Oh,
mistake.
okay. Good.
Thanks. Yes, yes. Thanks.
Right, right. That's fine.
Right, right. It is back to back. Thanks. Good. Very good. Right. So here the point is that therefore general multi-particle state, showing here two particle state as an example. In addition to the regular spin or helicity eigenvalue, there's extra pairwise eigenvalue, which again is a characteristics of the fact that the two particle is characterized by the both of the momenta. Okay, and so this is a general, say, two particle transformation rule for the two particle state. Okay, so this is the usual Wigner rotations, and there's extra U factor. And then we show in this paper how can we justify this fact more rigorously by actually doing explicit construction. And that works for arbitrary spin particle and arbitrary number of particles. So you may want to look at it. And then we also argue that you might wonder, okay, given the fact that I showed there is this extra quantum numbers to characterize two particle state or multi-particle state, can there be even more other quantum numbers? And we argue that maybe not, because if you try to do the same game with a three particle state and four particle state, you can easily realize that, say, with a three or more momenta, there is no standard reference frame in which you have non-trivial little group transformation. Okay, so two particle is the maximal number of momenta for which you can still have a non-trivial little group transformation. Therefore, a general multi-particle state will be characterized by sets of the one particle eigennumbers or quantum numbers, and then a set of pairwise quantum numbers or helicity. Okay, so this is the new realization. So now, but in majority of the processes that is occurring at the LHC, on the other hand, Q will be zero. Therefore, multi-particle state will be just factorized into product state. Okay, but there is one existing theory where Q is not actually zero. Okay, that theory is actually the theory with both electrically charged and magnetically charged particle. In that case, you can show that the Q, the pairwise helicity, is nothing but the product of the electric and magnetic charge. Okay, for the sake of the argument, let's consider even dion-dion pair. Okay, dion is basically a particle that carries both electric and magnetic charge. In that case, you can also show that the Q is basically cross product of the charge vector. This cross product of this charge vector. And in passing, let me just mention without a proof that given Q, which is basically fixed once you know the electric and magnetic charge of the particles, when two particles approach each other, meaning in state, when the fermion and the monopole approach each other, then relevant pairwise helicity factor comes with a plus sign. On the other hand, when two particles receding each other, meaning going away from each other, like in the out state, okay, then in that case, the phase here comes with a minus sign. Okay, I'm just mentioning the true fact, but if you want to know the actual argument for why this is the case, you can have a look our paper, or I can discuss after the talk if you're interested in it. Okay, now this gives us another cool demonstration. Okay, so this realization of the more general representation theory let us now derive what's known as a Dirac-Schwinger-Zwanziger quantization condition, or if you're more familiar, Dirac quantization condition. Okay, like I argue that for dion-dion pair, the relevant Q12 pairwise helicity is a cross product of the charge vector. In order to derive Dirac quantization condition or Dirac-Schwinger-Zwanziger quantization condition, we just note first that the Lorentz group is doubly connected. In other words, This just means for now is that 2 pi rotation is not actually 1. Okay, you start from the 1 point and you go around 2 pi, that you're not going back to the original point. You're actually going back to the -1 if you think in terms of SL2C structure. In order to go back to the original point, you actually have to travel 4 pi rotation. Okay, so let's say you just accept this fact for now. Then, given this phase, you can basically impose that condition. So if I do the 4 pi rotation, I should get 1. So that's basically the characteristic of the Lorentz group being doubly connected. Okay, so then this condition immediately gives you Q12 should be n over 2, where n is the integer, and that is precisely Dirac Schwinger Zwanziger quantization condition. But here I'm just giving you a purely asymmetric version of derivation. Okay, but that's just the byproduct. All right, so now I explain you how general multiparticle state, especially for charge pole state, monopole state, transform under Lorentz transformation. And again, it is in addition to a regular rotation, you get this pairwise helicity factor. Good.
Excuse me.
Yes.
At this stage, how do you know that you are assuming Q12 is a Lorentz invariant scalar?
It is Lorentz invariant scalar.
What's the argument for that?
Good. So one argument, quick argument is that remember Q is basically a function of charges, and charge obviously doesn't change under Lorentz transformation. That's an easy, quick, cheap argument. Another argument which required to understand this fact is that under Lorentz transformation, just like helicity of the particle does not transform under Lorentz transformation, even though the sign can change, as I show here, I just explained here, but the quantity or size of that thing does not change. That's another way of seeing it. But yeah, for now, you can just buy my argument saying that helicity, pairwise helicity, is basically product of the charges, and therefore Lorentz invariant. It doesn't change.
Thank you.
Okay, good. Any other question before I move on?
So one question is, what's the definition for in and out states for the dione states? So
yeah, so for dione, good. So you take the 2 dione with the electric magnetic charge like that. In state means that they approach each other, so that they are about to collide. That's what I mean by in state. Okay, out state is basically state after collision. They something happened and then they now moving away from each other and getting far and farther. That's what I mean out state. Is that clear, or there is a further question?
It's a symmetric under 1 and 2, right? So that's why I'm confused.
Sorry, can you say that again? I didn't.
So now it is, so Q12 is antisymmetric under the exchange of particle 1 and 2.
No, I didn't exchange. If you wish, this it's not exchanging it, right? So in other words, take the in state. Okay, take the in state, and then eventually they collide, and then now fermion pass through the monopole, and the monopole keep traveling. That turns into the out state. Well, I'm saying that before the collision, after the collision, there is a flip of sign for the pairwise helicity factor. Of course, I didn't show this how, but I just stated the fact because this will have far-reaching consequences eventually.
I see.
Yeah, but just for the sake of time, I didn't put any proof of this. But you can look at our paper, or I can discuss after. Good. Any other question? Okay, let's go move on. Okay, so now given the fact that we now understood how say fermion monopole state transform on the Lorentz transformation, now I can derive Lorentz transformation of the S matrix. Okay, so S matrix is basically product of the in state and out state. This is in state, this is out state. Here I suppress all the spin helicity indices or labelings, but they are there. I just don't put it in just to make the expression short enough. Okay, now in order to get the transformation of S matrix, now you just insert the 1, which is U dagger U. And we now understood the Lorentz transformation of this part, right? This is the Lorentz transformation on the multi-particle state. And this is basically a dagger of the other. And so here I just wrote the answer. We just said it is a product of the usual Wigner rotation, and then it is and then there is a pairwise helicity phase. And so this capital sigma is the sum of all phases for each of the pairs. For the out state, I do the same with the dagger, but I just inserted the minus sign, as I mentioned before, right? For the in state, for given Q, it comes with the plus. For out state, it comes with the minus. Okay. Once you buy this, then you arrive at this expression. So this is untransformed S matrix. This is a transformed S matrix. And then there is a product of the D for the in state. And then there is a product of the D dagger for the out state. And then there is this helicity phase for the in and out state, which comes with the same sign. Okay. Now I can just invert this expression, which I just quote here again, to get the now Lorentz transformation of the electric magnetic S matrix. Okay, so transformed S matrix is equal to untransformed S matrix times product of D dagger for the in state, and then a product of D for the out state, and e to the minus I times phase for the both in and out state. This is a helicity phase, pairwise helicity phase. So here I just wrote the explicit expression, but basically that just means that you consider all possible pairs of the fermion monopole. For each of them, there's associated Qs, and you just wrote down entire phase that are relevant. Okay, now this is for the, again, this phase is for the charged monopole pair or dion-dion if you want to do more general studies. However, I should mention that you have to include these phases for pair for either both in state or both in out state, but you never include this phase for the in and out pair, meaning, for example, fermion in the initial state, but monopole in the final state. Okay, there is no this pairwise helicity phase for that configuration. The reason is simply causality and locality, because how do you get this correlation of the fermion and monopole state? Because they coexist at one given instant of time. And then there is interaction through the electromagnetic interactions. But say past fermion and future monopole never had chance to talk to each other. Because if you want to say that they have talked to each other so far, that means that you're violating causality. So in any causal electromagnetic S matrix, therefore, there is a pairwise helicity factor for the in-state pair or out-state pair, but there is no such a pair between in and out state. And this signals already crossing symmetry violation for electric magnetic S matrix. So electric magnetic S matrix has many weird qualitative properties, right? For example, all of the S matrices we study in the LHC does have a manifest crossing symmetry. And without that, it's very hard. But we don't have that here. So this is another challenge. The first challenge was, how do we even understand asymptotic state, which I answered here. So this is the right asymptotic state and transformation property. Second challenge is that we don't have crossing symmetry, but we are going to overcome that too without too difficulty. Okay, but here the point is now we do know transformation property of electromagnetic S matrix. The only addition to the usual standard thing is this additional pairwise helicity phase. Good. Now I will move on to spinor helicity language. So before that, if you have any question, please let me know now. Good. Okay, so now I'm just going to review a little bit about the spinor helicity variables. Okay, so we just have talked about this equation, but I just written a slightly different notation. So omega is helicity half phase factor. And for now, I'm just going to consider massless particles only. I will include a massive particle momentarily, but for now, let me just talk about the massless particles. So here I want to consider a process like this. There is a 1-2 particle colliding with helicity H1, H2, and then there's a final state 3 and 4 with helicity H3 and H4. Okay, once again, omega is basically helicity half phase factor. And the usual S matrix transformation without the pairwise factor is basically this. So for in state, you get the helicity factor with a dagger. For out state, you get the helicity factor without a dagger. So I just wrote here. Okay, for out state, it's a helicity factor to the 2h. This is the correct helicity h3. For in state, I had omega to the inverse so that it basically incorporates this dagger for the in state. Okay, this is the standard S matrix without, say, monopole charge pair. Okay, now you note that the S matrix transform under Lorentz transformation as a Lie group tensor, not as a Lorentz tensor. Okay, remember momenta is Lorentz vector, but under Lorentz transformation, what you pick up is a Lie group phase vector, not like Lorentz tensorial structure. It is a Lie group tensor. Therefore, the language of spin helicity variable was motivated by the fact that S matrix is a manifest Lie group object. And therefore, we want to look for a variable to write down to construct S matrix, which is manifestly Lie group vector rather than Lorentz vector. Okay, and we can construct a Lie group vector out of the Lorentz vector first by, say, contracting with the sigma alpha alpha dot, and that just turns into SL2C matrices. For massless particle, determinant of this P slash of matrix, SL2C matrix, is a 0. That means that there is a 0 eigenvalue. That means that it is rank 1, meaning it is a 2x2 complex matrix, but there is only one linearly independent eigenvector of that. So I can just write down, therefore, this 2x2 matrix as a product of that single linearly independent eigenvectors. And so starting from the Lorentz vector, I'm getting SL2C vector. Okay, and under Lorentz transformation, this SL2C vector, which carries SL2C in this alpha, basically transformed with the Lie group phase vector, omega to the inverse. So lambda has a helicity minus half, and the lambda tilde has a helicity plus half. And the reason why these variables called the spin helicity variables is not obvious, because first of all, they carry SL2C indices like that. And then under Lorentz transformation, in addition to the SL2C matrices, they pick up the Lie group overall phase, so that they're the Lie group stuff. Okay, in other words, they pick up the helicity phase, and therefore it is characterized by both spinor, SL2C, and helicity or Lie group weight. That's why it's called the helicity, spin helicity variable. Okay, again, S matrix is a Lie group tensor, so I want to use these guys instead of the momenta to write down that explicitly. Okay, so here I just wrote the Lorentz transformation of S matrix for massless particle again, but then now I view S matrix as a function of these spinor helicity variables, which are manifest. They transform on the Lorentz transformation as a manifest Lie group vectors. Okay, now before I start talking about more, I want to first introduce how to convert in and out way of thinking about the scattering process, meaning you do have coming in particles and there's something coming out. I want to convert that language in terms of out-out formalism where all particles coming out. Okay, and this is useful, and also in majority of a spin helicity community, they exclusively use this out-out formalism. So I want to just talk about that a little bit. How do you convert that? In usual S matrix, without the particle monopole fermion, the S matrix does have manifest crossing symmetry. Okay, so crossing transformation is actually a symmetry of S matrix. So you can use that crossing symmetry to convert in and out object to the out-out object. But let me just explain briefly how you might be doing that. So how would you convert incoming particle into the outgoing guy? You can do that by doing a T to minus T transformation for incoming guys, right? If you reverse your time, what was approaching together will receding together, right? Each other. So this is basically time reversal transformation on this in-state guys. And by CPT variance, T transformation is equivalent to CP transformation. And under parity transformation, particle stays to be particle and antiparticle stays to be antiparticle, but helicity flips because left guy becomes the right and vice versa. And also 3 momenta flips too. On the other hand, under charge conjugation, particle becomes antiparticle or vice versa, but helicity stays to be the same. And then the energy becomes minus energy, right? Because if you remember in the like QFT 101, antiparticle either traveling opposite direction in time or they travel forward in time but carries negative energy. And this is that statement. Okay, so therefore, converting in and out into out-out by doing T transformation is equivalently combining these two operations, is to say that under that operation, you switch particle into antiparticle or antiparticle into particle, and then you flip the helicity, and then for momenta becomes minus of itself. Okay, so that's how you get the asymmetrics of out version of original in and out version. Okay, and we can do the same for monopole fermion asymmetrics. There, even though we don't have symmetry, we can use this as a formal way of converting a question here into out thing. The difference between standard asymmetrics versus monopole fermion thing is that in standard case, if you have asymmetrics that you want to compute like this channel, you can compute it, but then you can look at another channel, and that will be another physically sensible process going on there. In other words, crossing symmetry means that the asymmetrics analytic is an analytic function of momenta, which you can use either S channel or T channel or U channel. That's what it means by crossing symmetry. For asymmetrics for the electromagnetic process, you can translate the question into one another, but you have to remember that such a constructed asymmetry should be used only in one channel that is the same as original channel. But you should not use the same asymmetries in another channel because you don't have crossing symmetry. Okay, hopefully that's clear. If not, feel free to ask. Good. So now I successfully converted it in out to the out. So in terms of asymmetrics, that means that then remember, so for incoming guy, I'm gonna now flip the helicity factor in particular. So this is in and out version. So but for in state, I need to convert the helicity to opposite of that. So now it turns into that. Okay, so in out formalism, therefore, asymmetrics transforms on the Lorentz transformation according to this rule. Okay, in other words, if you transform, like for example, third momenta, compared to the original untransformed third momenta, you have to pick up corresponding little group phase. And it is now democratic to all of those guys because they're all coming out together. So they better behave the same way. Okay. Now, in terms of lambda tilde variable, spinor helicity variable, this transformation rule is now translated into the following equation. So for each momenta pi, so p1, 2, 3, for each of them, if I do the Lorentz transformation on the lambda, meaning basically little group rescaling, remember, lambda carried the helicity minus half, lambda tilde carried the helicity plus half, thereby rescaling by the omega inverse and omega respectively. If I do that, S matrix, which is the analytic function of lambda tilde, should pick up this overall little group phase, omega to the 2h. And this should be true for all of I, meaning if I have 4 particles, if I do it, it should satisfy for all those 4 particles. So therefore, mathematical statement about this equation is the S matrix is a function of lambdas and lambda tildes, which is SL2C singlet, meaning it does not carry uncontracted alpha beta guy. And on top of that, crucially, it is a homogeneous function of lambda tilde of degree 2h for each of I. Okay, so S matrix does have important effects about the spinor structure and then helicity structure. But here, the most important thing is this. So if you do the little group scaling for each of the lambda tilde pair, it should pick up the correct little group phase. That's the statement. Okay. Okay, let me move on. So for massive particle in passing now, because the p-square is not 0, p slash is rank 2. You have 2 independent, linearly independent eigenvectors. So p slash therefore should be written as 2 factors of lambda tilde. And you can package them together by calling 1, 2 as a sum in this I. And in fact, now I indices are contracted. In fact, this I index is nothing but SU2 little group index. And then on top of that, you have alpha prime, which is SL2C spinor index. Okay, so now if we have a S matrix or process with the 3 massless particle, with the 1 massive particle, say with a spin S2, we know how to construct the spin S representation out of spin half representations. Remember, each of the lambda is a spin half representation. So I can do the products, first of all, construct the product representation, and then the fully symmetrized part of that is the spin S representation. So that means that the S matrix with some massive particle must have fully symmetrized SU2 little group index. And in fact, 2 S of them to have S spin-s particle. Okay, and then on top of that, for massless particles, it's usual. There's the helicity indices or labels, if you wish. All right. So then I will be using often this fact. So previously I said that the S matrix with the massive particle has a fully symmetrized SU2 indices, but you can trade that with the fully symmetrized SL2C indices by stripping out massive variables. Remember, the combination of this I call the massive variable. And then I can strip out 2S of them to trade between fully symmetrized SU2 index with fully symmetrized SL2C index. So I will call this version to be stripped S matrix, which I will use most of the time. Okay, and for massive particle, there's no actually distinction between alpha and alpha dot indices, unlike in the massless case where it was crucial because one carried helicity minus F, the other carried the helicity plus F. But what I'm saying here is that for massive variable, there is no actual importance between alpha dot because you can use equations of motion. This is basically Dirac equation written in terms of spinor helicity variables. So for example, if you had alpha prime index, you can rewrite in terms of alpha index by just using this equation. So you can choose to express your stripped S matrix either in terms of all alpha indices or in terms of all alpha prime indices. So today I'm just going to be using only all alpha convention, just for the sake of it. Okay, last thing about the massive case is that, like I said, the massive variable carried is SU2 index. And just like a Dirac fermion, which is a massive fermion, has both left-handed and right-handed guy packaged together. Just like that, a massive variable can be written as a linear combination of the two massless variables. Okay. In other words, you can expand this guy into the basis of SU2 basis, and with the coefficient, which is basically massless variables. So there's a lambda and lambda tilde. Therefore, likewise, there's a pair of the lambda tilde, which is a one pair of massive variable. There's another eta tilde, which is the second pair of massless variable. In fact, they are parity conjugate to each other. In other words, if lambda had the helicity minus F, effectively like a vector going into the positive direction, eta being a parity relation conjugate of that has opposite helicity. So if lambda had a plus helicity, eta has opposite helicity. And of course, tilde guys always have opposite helicity. But if you don't want to get confused, just to make sure lambda, eta carry opposite helicity. Just like you can contract left-handed divided fermion and the right-handed divided fermion to write down mass term, this is basically that spinor helicity version of that statement. All right. So so if you want to take now massless limit or high energy limit, it's effectively taking Dirac fermion and say they split into two massless Weyl fermions. So either you turn that into left-handed Weyl fermion or that turn into a right-handed Weyl fermion. Therefore, operationally, within the context of S matrix, if you had S matrix constructed out of massive variable, taking high energy limit or massless limit is effectively either choosing or taking this to be this lambda variable guy, or you take this, the parity conjugate version of that. So that will effectively operationally taking massless limit. Okay, so that's so much so about the massless and massive variables. Let's come back to the electromagnetic S matrix again. Okay, so this is the equation I told you already. So the transformed S matrix for the electromagnetic S matrix is untransformed guy with the product of D dagger for the in, product of D for the out, and then there is a little pairwise literal phase. Okay, now let me write this in terms of out formalism. And under that, remember helicity flips for the in-state, for example, so that becomes the same. So for both in and out state, they have the same form of the little group scaling. For the helicity, so pairwise helicity, you get accordingly the corresponding phase, but with the minus 2q instead of the plus here. Okay, because out state comes with a d, which is basically e to the, or basically omega to the 2h. but the pairwise guy comes with a minus. That's why I have a relative minus. Okay, so what's the situation here? So I had fermion 1 monopole, and then fermion 3 monopole, and then there's a helicity for this guy, and then there's a helicity for that guy. So for the regular one-party helicity, they have to satisfy this rescaling under the scaling of the lambda lambda tilde. But in addition to that, this pair had the Q12 Lilligre phase, a pairwise phase, and then another phase for the final state. So for each of these guys, the S matrix for electromagnetic process should also pick up the correct pairwise helicity factors. Now the question is, okay, we now have understood that this is the form of the transformation. The question is, we know how to make this happen, right? Because that's how regular spinor helicity variables are constructed. Regular spinor helicity variables are constructed in such a way that under Lilligre scaling, they pick up the correct helicity phase. That's how it is constructed. Now the question is, how are we going to saturate or satisfy this condition? Okay, that's the additional condition on top of usual regular S matrix. And how are we going to satisfy this thing? And we know that regular existing lambda lambda tilde will never fulfill that because they are designed such that they only satisfy these conditions. Therefore, we need some new spinor helicity variables. And that is why we need something new, which I call pairwise spinor helicity variables, to which I will now move on. Is there any question before I move on? Okay, good. All right, so then how do we construct that? So first recall the pairwise Lilligre group is U1. Okay, therefore associated quantum number is a helicity, not a spin like SU2. And therefore it is a pairwise helicity. Therefore we know that the corresponding variable should be a variable associated with some null vector, right? P squared equal to 0 vector. Okay. On top of that, we know that the pairwise helicity is the characteristics of or intrinsic property of a pair of a Pij, right? Pair of the fermion momenta and monopole. So therefore, the idea here is that given Pij, and both can be, say, massive. It doesn't matter, okay? Either fermion can be massless, or monopole can be massive, or both can be even massless, or both can be massive. Doesn't matter. But here, the point is that we can construct out of those pair of momenta, the null momenta, which we call a flat variable. This looks like a B, but it's just a flat. Okay, we can construct a flat variable such that it is a null. Okay, in other words, we start with some linear combination of the, say, fermion monopole momenta, which again can be either massless or massive, doesn't matter, in such a way that we want to determine this coefficient such that they are null vector, and it does admit nice, good limiting property as we send the mass of the one or both to be 0. And we want this because eventually we want to have a formalism which is valid in the fully relativistic situation as well. So that's why we impose this condition. So if you try to find a solution to this property, you ended up finding basically two independent solutions up to normalization factors. Here I'm giving you two solutions, which I call P flat plus and P flat minus. There are two solutions. Okay. Which is, again, as I promised, just a linear combination of fermion and monopole momenta. Now, for the rest of my talk, I will be thinking like the first guy is a fermion, and the second guy is a massive monopole. Okay, but again, this formalism works arbitrary case. But here I'm just constraining myself to the say I being fermion and then J being monopole. And in fact, I will be interested in mostly massless fermion case. So I want to study what happens if I take the fermion mass to be 0. In that case, plus variable becomes the same as the fermion momenta, and the minus variable becomes the periodic conjugate of that fermion momenta. Okay, remember there was a lambda in the massive variable and associated eta. Okay, so plus pi plus and then minus variable in the massless fermion limit becomes either fermion or periodic conjugate of the fermion momenta. So that's why you want to remember. Good. Now, given the fact that I have successfully constructed a null vector out of a Pij, now I know what spinor helicity variable I want to look at, because now the Pij either plus or minus are massless momenta. Therefore, I know they can be the corresponding p slash is a product of the spin helicity variables. In fact, these spin helicity variables is guaranteed to pick up correct pairwise helicity factors, like so. But instead of going through that, let me just say that is the case. But I can come back to this point and discuss just for the sake of time. Okay, so now I have successfully introduced and constructed necessary extra spin helicity variables, which remember is not something that I throw in arbitrarily, but I actually constructed from a given pair of momenta. Okay, so that's the important part. Good. All right, now let me just state the rules of the electromagnetic asymmetrics. But before that, is there any questions? Is there any question? Good. So now you want to really wake up and then focus, because now, once you understand the rule, this part, then you more or less get the picture. Okay, so let's say I'm interested in computing this scattering process. Okay, so fermion F1 collides with the monopole M2, and then what comes out is a fermion F3 and then monopole M4, and with some pairwise helicities in state and out state. What are the building blocks? Okay, what are the building blocks for my electromagnetic asymmetrics? First of all, for each massless particles, for example, fermions, I know there are corresponding lambda tilde, the regular spin helicity variables. And the angular bracket, like I said, has a minus helicity, half helicity, and then square bracket has a positive helicity. So I'm just reviewing that. For massive particle, let's say my monopole is a massive or even spin in general, then I show that there is a corresponding massive variable, which can be written as a linear combination or sum of both two sets of massless variables. And for the pairwise helicity, I introduced that for each pair, I construct the pairwise helicity. And remember, there's a plus variable and a minus variable. In the massless fermion limit, like I said, plus variable is basically regular fermion variable. Minus variable now turned into a parity conjugate of that. And under pairwise little group transformation, this guy pick up, just like a fermion, pick up the minus half helicity, and then negative variable pick up the parity conjugate version of that, therefore positive. And then, of course, the square bracket satisfies opposite relation to the angle bracket. Good. So these are the building blocks. Now I have well-defined building blocks. Then what are the rules? So I already talked about for the regular massless helicity case, under the rescaling, little rescaling of each of the lambda tilde pair, they should pick up the correct regular helicity factor. For the massive case, I said that you better see fully symmetrized SU2 indices, 2S of them, or you can strip out the massive variables to say that it is only SL2C guy. The advantage of going this way is that unlike this guy is a purely SL2C tensor. This is both SU2 thing, and then there's also SL2C structure. So it's mixed up, but this is a purely SL2C object, so it's easier to deal with. That's why we want to consider this object most of the time. So that's a regular little group transformation property. Under pairwise, now you just rescale the same way, but both plus variables and then minus variables accordingly. Then under that, you should pick up the correct pairwise helicity factors. But remember, in the regular case, you pick up the plus 2h. In the pairwise case, you pick up the minus 2h. And then it should be SL2C single, meaning in this language, entire SL2C indices should be completely contracted. But once again, I will often talk about the descriptive version. In that case, the only uncontracted SL2C indices are this massive part. Good. And this is standard rules, but there is additional rules, which turns out to be very important, actually. First of all, I will be interested in local asymmetrics. Like I said, remember the motivation is that can I construct the fermion monopole scattering process, which is manifestly local and Lorentz invariant and unitary? Here I'm posing locality, but the locality in the language of asymmetrics is basically saying that the asymmetrics is analytic function of momenta. And in terms of a spin helicity variable, that just mean that you don't see 1 over some contraction of the spin helicity variables. Okay, that's just like 1 over p or p squared. That's the signal of the non-analyticity. And I will talk about partial wave decomposition. In other words, a total S matrix can be sum of some S matrices in which in state and out state has total angular momentum J. So you can decompose full S matrix in terms of S matrix of fixed total angular momentum in and out state. So there's an in state and out state. You want to look at S matrix of a total angular momentum J. So I will do it momentarily, this partial wave decomposition. And then we will also make sure that my S matrix is unitary in this sense, but eventually I will get the partial wave version of the unitary equation, like so. And in some cases, we will need some dynamical input, okay? Remember, S matrix is not solving dynamics, okay? S matrix will not completely solve dynamics all the time. Some cases, it does actually quite like almost solve dynamics, which I will show later. But it's not guaranteed that S matrix program alone can completely fix entire dynamics. So in some cases, we will need some amount of dynamical input in the form of the phase shift. Remember, S matrix, like partial S matrix, can be written as a phase, and that this phase is a phase shift. Okay, so this will be another important ingredient on top of this rules for the little group or Lorentz transformation rules. All right, so having said that, now I'm moving on to actually using these rules to do something. Okay, before I do that, if there is any question, this is time for asking that. Okay, it's good. So here, in our paper, we actually constructed all possible, the most generic 3-point electromagnetic S matrices. But here, I will just only focus on one case where there are 3 massive particles. In principle, you can completely determine up to proportionality vector. For example, 2 massive, 1 massless, and 1 massive, 2 massless, even 3 massless. That's possible. But here again, I will just focus on this, which will be used later for studying 2-to-2 scattering. For each of the case, I should say that there is associated some sort of rules or constraint on these quantum numbers, helicity, spin, and whatnot. And these are what I call generalized spin helicity selection rules. These are kinematic selection rules. Once you specify quantum numbers of individual particles and also this pairwise helicities, then angular momentum conservation locality tells us that there is some constraint on possible choice of quantum numbers. So for example, in the case of 3 massive case, this is the equation. This is the condition that is derived by trying to construct this amplitude. And the statement is that the absolute size of the pairwise helicity, so I'm thinking of going that way, pairwise helicity should be equal or smaller than sum of the spins. For example, one way of using this equation, for example, can be that let me consider like theory of dyons in such a way that Q23 is non-zero. And then this selection rule tells me that the scalar dion, meaning S1 is 0, cannot decay into pair of a scalar dions, meaning S2, S3 is 0, because it cannot satisfy this equation. So this tells me already some sort of forbidden rules. Okay, and then other cases you will get other kind of even more number of selection rules. Let me quickly say that our result, which we derived all these examples, are generalization of Nima, Yuting Huang, and then others result, and this reduces to correctly in the limit where Q equal to 0, meaning non-magnetic case. And in fact, it is stronger than non-magnetic case. And again, successfully reduces to the non-magnetic case in Q equals 0. But if you're interested in, you can have a look at our paper section 4 about this discussion. So what's the point of talking about S matrix of a 3-point function? Okay, one obvious thing is that you might wonder whether you can compute the decay process because this diagram suggests decay process. But importantly, in our case, we're going to use this as a trick or method of doing fully relativistic partial wave decomposition. What do I mean by that? So here's S matrix. Okay, there's some in state, there's some out state, and then I want to look at the initial state such that the total angular momentum is J. And how do I get that part, right? How do I get like total angular momentum J part? How do I select the part? And you can think about that way. Think about this decomposition as follows. So let's say there's an initial and final state. Oh, sorry. There's a pair of a state in the in state. And the fact that in state carries total angular momentum J means that they can convert into some intermediate state, possibly massive, with a total spin J. Okay, so basically, effectively computing this 3-point function is effectively figuring out, given arbitrary in state, what is the probability of getting a spin J state out of that. Of course, importantly, like I promised you, I'm going to be doing local process here. So I'm not going to be putting any pole associated this in state, so intermediate state. Again, I'm not saying that there will be physical intermediate state, but I'm just visualizing or imagining of doing this partial wave decomposition as if there is a two-particle state turning into a state with a total spin J. So therefore, importantly, I will not put the pole at all for those guys. So this way of thinking about it, of partial wave decomposition, is basically we can easily do the partial wave decomposition once we do have a 3-point function. So that's the approach. Okay, so then how do we do that? So instead of actually showing you exactly how to do that, let me skip this slide. So basically, I want to compute this thing. Instead, so here are some details. You can look at it, but the answer looks like this, basically. Okay, so let me quickly say that. So I want to construct S matrix corresponding to the 3 massive particles. So like I said, stripped S matrix has a 2s1 SL2C indices for the, say, spin S1 particle, and likewise for the S2 and S3. Okay, this is SL2C tensor. The question is, what is the basis for the SL2C tensor? The answer is these two pairwise spin helicity variables. Okay, they carry alpha alpha. Okay, so then the general S matrix of this 3-point will be some power of the positive variable and then some power of negative variable. There are 2 conditions for this thing to satisfy. First, the entire number of indices should be the same as entire number of indices I want. So that's the first condition. So A plus B should be equal to sum of all these things, which I call 2S set. Also, this 3-point function is basically, doing this, and then there is a Q23. So it should satisfy correct little group helicity phase. So that's the second condition. Okay, remember, positive variable has a minus half pairwise helicity, and minus variable has a positive helicity. So that's why it's a minus here, is a plus here, and it should be minus 2Q. So if you'll solve this and then get the answer, because this is a simple linear equation, you can plug into the A and B. This is the answer, basically. Okay, so you can construct this thing, and we're going to use that to talk about the partial wave decomposition momentarily. Okay, good. All right, now I'm moving on to the partial wave decomposition, and if you have a question, feel free to ask now. So I'm almost there before I talk about the physics of it, but I still need a little bit more, just a little bit more preparation. But again,
before you proceed, could you show the slide about this selection rule for?
Yeah. No.
Yeah, this one.
Yeah, here.
So here you say that if Q23 is not 0, scalar dione cannot decay into a scalar dione pair. So usually I think the most when we consider if certain process can happen or not, we consider the energy momentum conservation, total angular momentum conservation, and any conserved charge. I mean, if there is a conserved charge, we have to check the charge conservation.
Yes.
And also Bose symmetry, or the statistics theorem, right?
Yeah. Yes, that's right.
And so now here, when you have a monopole diones, so what kind of extra conservation?
Yeah, so it is the like it's a generalized angular momentum selection rule. Remember in
What's
the
the angular momentum?
yeah, it is actually angular momentum selection rule, but because of this extra pairwise U1
Mm,
helicity,
mm.
it makes it it give you a stronger condition. In fact, in usual without that, you're not going to get any this selection rule. Pretty satisfied.
Okay. Then I think I vaguely remember that in soliton physics, the internal isospin also contribute to the total angular momentum, something like that.
Good. So in
So
fact, there is a way. Yes, there is a way of understanding this Q in terms of internal isospin. So there is this a spin from isospin by Tuft and others, and then the Jakiv.
mm-hmm.
Okay, that thing is basically exactly this extra U1 helicity factor in the language of S matrix, if you want.
Okay.
Yeah,
Okay.
it is already built in this our S matrix
I see.
language.
Okay.
Yeah.
Great.
Yeah. Okay. Good. Okay, so now partial wave decomposition. So what's the point here? So given full S matrix, I want to write that as a sum of the subchannels, where in each channel, the initial and final state has some specific total angular momentum. Of course, in and out should have the same because by the total angular momentum conservation. So I want to write the S matrix as sum of S of J, where Sj is again with a particular angular momentum. In electromagnetic S matrix, total angular momentum has a regular angular momentum thing and then spin. But on top of that, we have been dealing with extra pairwise U1. In fact, this is isospin contribution, Pyongwon, and that turns into as if it behaves like a spin. Okay, but it is same thing. So anyway, so in electromagnetic process, total angular momentum has three pieces. And the goal is that to do this partial wave decomposition in a completely fully relativistic way, meaning I want to do the partial wave decomposition for Poincare group rather than just SU2 rotation group. So that's the goal. Here is the summary or answer to that thing eventually. So this will be written as a three factor, sum of three factors. First is a coefficient, and this is a matter of choice. And we're going to in fact choose this coefficient AJ such that unitary equation for the original S, it turns into nice equation for this MJ. So in fact, we're going to choose this particular coefficient such that the unitary equation for S is equivalent to unitary equation for this MJ for each sub-channel J. Without, for example, other coefficient, but it's a uniquely one. That's the goal. And here, the most important piece is BJ. Okay, this we call a basis amplitude, and this is basically eigenvalue or eigenfunction of the total angular momentum. So this is basically make sure that the subchannel does have a required property that in and out state has a total angular momentum J. And encodes, in fact, kinematics of the problem. Okay, and it encodes entire angular dependence of it. And this is what provides us non-trivial selection rules. And the remaining factor, which is a function only of a PC, the center of mass energy, is basically encodes some dynamics of it. Okay, and this we call reduced matrix element, but name is not important. But the important point here is that this MJ is completely independent of any angular dependence. And in fact, this is related to the phase shift that I was mentioning earlier. So what's the goal? I know I want to decompose S matrix as a sum of the J channels, and then the base amplitude basically captures entire structure in such a way that it satisfies required angular momentum conservation and the properties. And then there is a coefficient, and then there's remaining factor that's basically some dynamics. Here is the fuller picture of that. So S matrix can be written as a sandwich of S operator between in and out state. Okay. Here, this is individual, like there is say some number of in state, like with the momentum, spin, and then other indices like pairwise helicity. And likewise, there's a similar thing for the final state. Now, I want to insert the complete set, but this complete set of bases is now in terms of total angular momentum instead of individual spins and angular momentum. Okay, and this overlap, meaning if you remember, if there were J1, J2 say representation, I want to get total angular momentum J1 plus J2 say representation, or I want to get the J1 minus J2 representation. This overlap is precisely Clebsch-Gordon coefficient, but here I'm doing it for Poincare. And for out state or final state, you have a similar overlap too. But in the middle, what you have is that the S operator sandwiched between eigenstate of the total angular momentum. And you notice that this is nothing but the S matrix with a particular total angular momentum in state or out state. Okay, so this is basically what's encoding the some dynamics of it, which I called reduced matrix element of MJ. And then product of these two factors, here we're writing here, is precisely given some in-state with some spin helicity turning into some state with total angular momentum J. And this is precisely the factor I was talking about. And the product of these two is nothing but what I call the base amplitude. And the remaining is some MJ, reduced matrix element. Okay, so that's the idea. So because you got the picture, let me skip through it, but except the fact that the BJ is again the this factor for the in, that factor for the out. And then we know how to compute this 3-point function, for example. I talked about one case before, and then I will talk again about this momentarily. Important point is that this BJ, like I promised, is an eigenfunction of the total angular momentum J. What do I mean by that? Poincare algebra has the two Casimir operators, meaning operators that commute with all of the generators. Okay, one is the p square of the total angular total momenta, which measures the mass of the state. The second is the square of what I call the pseudo Pauli-Rubensky pseudo vector, which is defined as this, which measures total angular momentum of the state. In fact, you can show that the base amplitude constructed as a product of these two, in fact, does satisfy this property. And in fact, it correctly constructed such that this is uniquely total angular momentum J basis. Okay, good. So now unitary. So now I talked about this version of the partial wave decomposition, but let me just mention in this part that this unitary equation for original S matrix, I'm not going to be talking about the scattering amplitude, okay? Remember, S matrix in the usual case is a 1 plus I times T, and then this is S matrix, this is the scattering amplitude. In electromagnetic case, this is not actually true. This is already one of the very non-trivial thing, because as I will show, in its lowest partial wave, meaning smallest possible J channel, the forward scattering, meaning like, for example, fermion with a negative helicity, if you throw in, cannot come out with the same helicity. So one cannot happen. So in fact, so in this situation, it is not a good idea to talk about the scattering amplitude, but rather we're going to just directly talk about the S matrix. So I don't want to look at the unitary equation for T as usual, like I times the imaginary of the T is equal to, remember, the T dagger T. I'm not going to be using this because that's not the right one. Instead, I'm going to be using just original unitary equation for S, and then I want to get the corresponding equation for this decomposed version of that. In fact, I want to get the unitary equation for M, but let me just tell you that you can do the job such that the unitary equation turns into this equation. Okay.
Excuse me.
Yes.
Me. So here you say, but in the usual case, this one means a kind of no scattering, right?
Kind of what again?
No, there is no scattering. I mean, for example, if you turn off the interaction Hamiltonian,
yeah,
there is no scattering. Still S equal to 1.
So e to the is in the Hamiltonian picture is 1 plus e to the. Then you can do the. In fact, yeah, it includes. Usually, this includes the no scattering. You're right in a sense that here's the monopole. If I throw in a fermion with say left-handed fermion, no scattering, or more general term is the forward scattering, is that there is always a chance to come the process that what's coming out is with the same quantum number.
Yes. Yes.
Okay. What I'm saying is that in the electromagnetic case, if you throw in a fermion with the left-handed guy, okay, in its lowest partial wave, meaning in the J is a minimum state, this is not possible. You always have a flip of the helicity. It's a strange. I understand. Of course, this is non-trivial statement, and then we, of course, we got confused and talked about it. Think about it. But remember, one is one. But if you try to write down one in terms of expansion of the, for example, spherical harmonics, it should be the sum of entire L, right? Because if the plane wave goes through it, or with respect to some particle, single plane wave contains entire tower of the angular momenta.
Right.
So it's not enough that the some angular momentum goes pass through freely. You have to make sure entire angular momentum tower should pass through without getting affected. But what I'm saying is that in the case of electromagnetic case, in the lowest partial wave, in fact, higher partial wave will go through without getting affected, but the lowest partial wave always get the flipped, helicity flip, and this is what makes it not possible to have a full one. You are missing one piece in this sum.
So what I'm saying is that I guess what I'm saying is that in the usual formulation within the perturbation theory,
Yeah,
and S matrix is a time ordered product of the interaction Hamiltonian.
Yep.
In the interaction picture.
Yeah.
And when we put the when we turn off the interaction Hamiltonian, S is simply one. So are you
True.
saying that if you have a fermion and the magnetic monopole system, you cannot turn off the interaction Hamiltonian, or the usual perturbation pictures totally break down?
Yeah, good. So that's the right statement. So in the electromagnetic asymmetries, like I said, this process goes through by very, very non-perturbative process. It's not like I can write, this is wrong equation, 1 plus something. There's no perturbation expression I can ever talk about for this process. And the interaction between these two, fermion and monopole, never turned off asymptotically. And in fact, interaction size is controlled by EG, which by Dirac's quantization is integer number, meaning it's a 1. It's a completely non-perturbative process. So it's very counterintuitive, I agree, but nonetheless, it's a true statement.
Then in that case, whenever you consider monopole, you have to consider monopole plus 1 photon, monopole plus 2 photon, etc. Because this state.
Yeah, very good. So that part of the question, we don't have a full answer yet. So you can ask the same question even in the standard example where the soft photon process can be properly resummed. And in fact, that's one recent work by the Harvard group, right? Trying to make sense of the S matrix with the very soft emissions.
Yeah, but in that case, you still, I mean, the coupling is small, but the monopole, magnetic monopole case, the coupling is what?
Yeah, it's just EG, like n over 2.
Yeah.
Yeah, what I'm saying is that we are not computing, like, for example, tree diagram in any sense. We are not. So if you start thinking about this diagram, then yeah, you are right. You have to resum all this thing. But what I'm trying to do here, is actually I'm just writing out this answer consistent with the locality and Lorentz invariance and this and that. I'm just writing that full answer like a one shot. I'm not trying to like doing this job as a resummation of any version. We are just trying to write down the answer and once.
So I understand that point, and then maybe my question would be whether magnetic monopole can make a good, well-defined asymptotic state or not.
So good. So yeah, that's a important question. I can say two things. If you want to study like magnetic monopole with G as a one particle state, for example, let's say your universe has only monopole without electrons. Then if you study the transformation, the representation of Poincare group, it behaves just like a regular one particle state. Okay, it just trivially satisfies all the property that you know. The non-trivial thing happens when you put both monopole fermion together. And there, I argue that we understand how this guy transforms asymptotically. That's this little group phase, pairwise little group phase, and this and that business.
Okay, I maybe we can talk later. Yeah, thank you.
Yeah.
You
Okay.
go ahead. Yes.
Okay. So here I will just state the fact that the unitary equation for original S matrix can be transferred into the unitary equation for this reduced matrix element, assuming the spectrum of the theory is basically a pair of a fermion and a monopole. So a fermion of either helicity and then monopole. Okay, assuming this, then unitary equation for using some properties of some detailed structure can be just written as mj dagger is equal to 1. When I say 1, remember the state consists of fermion and monopole and fermion of either helicity. So basically, 1 is a 2 by 2 matrix of helicity minus 1 half fermion or plus half fermion, and likewise here. So 1 means 1 in this 2 by 2 sense. Okay, so then this will be the unitary equation I will be using to talk about. Okay, so let me now, hopefully in the next 10 minutes or so, discuss at least the lowest partial wave case, and then leave the higher partial wave case out. So now let's study 2-2 scattering. Okay, so I just throw in some fermion and a collision of the fermion and the monopole, and then there's a fermion monopole comes out. And then there is associated a pairwise helicity Q and Q here. Okay, now the S matrix has this form. Again, this is basis amplitude, which fulfills the correct Poincare version of the partial wave decomposition. Coefficient we chose such that unitary equation for M is clean and nice. Now, first let's consider massive fermion case. Okay, it's easier. So I'm now consider massive case, and then I will reduce to the massless case and to get the answer out. So let's first talk about the quantum number. So total angular momentum has an orbital, usual, and then a spin, and then a pairwise U1. And then a representation theory of this part can be done, and you can show that the quantum number for these two combination is size of the Q, Q plus 1, Q plus 2, etc. So total angular momentum, therefore, for spin half case is either symmetrization of this L and half or anti-symmetrization of these two. Okay, so therefore, total angular momentum quantum number is the Q minus half, Q plus half from this, and then Q plus 1 and the plus minus 1 from this, and then Q plus 2 and then plus minus half for this, and so forth. So you see that the smallest possible angular momentum is the Q minus half from this, and then there's a whole chain of higher values. So when I call lowest partial wave, I mean this, and then there's a higher partial wave part. And then this part, I will discuss how to construct S matrix for this lowest partial wave channel. That's the goal. Okay. So how do we construct this? This is basically product of this in state with some intermediate state with total angular momentum J, and then that with the J with this final state. So basically the product of these two factors. And then this Cj, which we talked about it, but the answer looks like this. Okay, so let me come back to this equation later on if you're interested in how, because it's very quick. If I have 5 more minutes, basically I can explain easily. But for now, let me take this as granted. Okay, so C is a contraction of the massive fermion variable of this guy with there's a pairwise variables, and there's a QQ times 1 factor. And therefore, basis amplitude is a product of these in and out parts. So it's a product of these two factors. So there is a that from the in part, and there was a that part from the in, and then you will have a similar term for the out part, and this is out part. This is contracted version of that. Okay, and then I just put it in the proper factor of 2p so that it makes this bj to be dimensionless quantity. Good. So here is the therefore basis amplitude for Q positive answer. Okay, and then now let me take the massless fermion limit. I told you that the massive variable is the sum of the one kind of variable and another kind of variable, which is a parity conjugate of lambda. And I also told you that when I take the massless fermion limit, the positive pairwise helicity variable becomes that of a fermion. In other words, in terms of spinor helicity language, this variable in the massless fermion limit is equal to original fermion variable. And then I told you that the minus variable is becoming parity conjugate of the fermion variable. That means the minus variable is eta. Okay, so this is basically remind you of the fact I already told you. So how am I going to now take the massless limit? So given a massive variable, either you take the lambda limit, meaning it becomes the original fermion variable, or you take the eta limit, meaning you take the this limit. Okay, so that's how you take the massless limit. So now let's study this. So let's first look at the helicity non-Fourier process. In other words, you have f going into the f. But if you do this is in and out picture. If you do the out picture, helicity for the in part should be flipped. So basically you're talking about plus half in the in state and minus half in the out state. Okay, so taking this limit is basically for the in state, you take the eta for the massive variable, and then you take the f, original fermion variable, for the out state. So you take this to be eta and this to be f prime. And then I note that the plus variable in the massless fermion limit is equal to f. And then the contraction is antisymmetric. And therefore, if you contract the same guy, that's 0. So for this helicity non-Fourier process, I just show that this is 0. Let's do the same thing for this guy. So now I take the positive helicity guy in the in state and the positive helicity in out state. Therefore, it is a helicity non-Fourier process. Again, let me translate this into the out language. That means that for the in state, I need to flip the helicity. So I just have a minus helicity. So taking this massless limit means that for the in state, I have to take the f variable. So here, instead, I take the f variable. For the out state, which is the positive, therefore it's eta variable. So I have to take eta variable. Now, eta contracted with the positive variable is non-zero. But again, positive variable becomes the same as a fermion variable in the massless limit. So I contract f with the f. That becomes 0. So once again, this is 0. So I just showing that by the generalized spin helicity selection rules. In this case, in the lowest partial wave, there is no helicity non-Fourier process going on. Then how about the helicity flip case? Again, let me consider this example. So let me take the case where f turned into, so in other words, the negative helicity state turned into positive helicity state. So again, in the out formalism, that means that I have to take eta for the in state and then eta for the out state too. So now this, I'm taking eta and the eta prime. And then again, plus variable becomes f. So you can show that the contraction of eta with f is actually non-zero. In fact, it is actually 2pc. So this is non-zero. In the case of Q positive, what happens to the other kind of helicity flip process? Now, in other words, for the in state, I take instead a positive helicity state, different, and that turned into the negative helicity state in the final state. Again, in the out formalism, I have to flip the helicity, that becomes a minus. So in this case, I have to take f and f both in the in and out state. So if I take f here and f prime here, that's 0 because I'm contracting f with f, f prime with f prime. So that's 0. So while none of the helicity non-Fourier process can go through, helicity flip case, in the case of positive Q, while one of them is 0, the other can go through. Okay, so with the positive Q, negative helicity initial state can go through. So lowest partial wave process then therefore tells us that there is only helicity flip process, and it's not that both can go through, but only one of them can go through. In fact, now you can compute this angular dependence by actually computing this part, because we have explicit expression for these flip variables, flat variables. In fact, the computation gives us this. So in other words, if you collide through the z plus z direction and then that scatter out with angle theta, what I'm saying is that this basis amplitude is basically sine theta of 2 to the power of 2q minus 1. You can do the same exercise with the negative q value. In fact, in this case, only the second process will go through and this will not go through. And also, there is no helicity non-Fourier process. So the answer is the same, but the angular dependence is exactly the same. So with this answer, now you can look at the original S matrix, which had a coefficient AJ. which now become proportional to 2q. And then I just determine the angular dependence by analyzing basis amplitude. And then there is this factor, which encodes the dynamics of it. Okay. In fact, you see that if you turn q equal to 0, entire asymmetry vanishes, right? Nothing happens. And you might say, how can that happen? And that happened because the q is equal to, j is equal to q minus f, right? And then, of course, if I set q equal to 0, of course, the total angular momentum cannot be negative, and therefore nothing should happen. And it is consistent with what I'm saying here. Now, based on this, now we can even determine entire asymmetrics, not just having this unknown factor. I'm saying we can even determine that factor almost exactly. So for that, now we use unitary equations. You remember, partial wave unitary equation is to say that mj dagger is equal to 1. 1 in this 2x2 sense. So let's first look at I is equal to minus f and O equal to minus f, because I'm just looking at this upper part. So I just take I equal to minus f and then O equal to minus f out. So in other words, in is a minus f, out is a minus f. Now, from the analysis of basis amplitude, we learned that the only non-vanishing process is when this actually flips into. So the only thing, so I need to sum over m in principle in this equation because I'm inserting complete basis. But the only thing that survives is actually m is equal to plus half. Okay? Because minus half minus, I showed that that's a 0. Therefore, unitary equation tells me that the absolute value square of m minus a half is 1. If you do the same thing for the lower block, plus half, you get the similar equation. Okay, what does this mean? What this means is that this and that separately have a magnitude of 1. What does that mean? Remember that these two processes cannot occur simultaneously because that corresponds to physically different processes. Okay, and even physically different theory with a different Q. Therefore, for each of the asymmetrics, I know that this is equal to 1. So therefore, I know that this is almost just a 1. In fact, just a phase with the modulus 1. But whenever we are interested in, for example, cross-section, which you square this guy, therefore you completely even fix this guy. And therefore you completely determine entire asymmetrics into the lowest partial wave. Remember what I have done. What I've done is that I just assume the spectrum consists of the fermion and the monopole. And then I impose the generalized angular momentum conservation properly. And then I impose the locality unitary carefully. And what I learned is that without even specifying full theory, I completely fixed asymmetrics in its lowest partial wave. That's the achievement. In fact, there was a full, rather tedious quantum mechanics calculation done by Kazama, Yang, Goldhaber. If you look at their paper, I mean, it's not that easy to decipher what they are trying to say. Okay, but they use a lot of math techniques. But then in the end, if you're lucky, you can find their answer. And in fact, this is exactly what they actually say, including even these factors. So this is basically reproducing full quantum mechanical calculation. But now I'm just using spin helicity formalism. And then this is almost comes out as an easy, simple spin helicity selection rule and unitary. Okay, so with that, because I'm going over time, I was going to talk about the higher partial wave, but let me leave that for now, and I come back if someone interested in. And with that, let me just conclude. So I argue that there is no satisfying local and unit Lorentz invariant description for electron and the monopole process. And then I said that the modern on-shell asymmetrics program can help this hard problem because there's no Lagrange description. And maybe we can solve it by on-shell asymmetrics method. In fact, I argued that the generalized multi-particle representation of extra pairwise helicity. And in order to handle this one, I introduced extra pairwise spin helicity variable, which are additional building blocks for the electromagnetic asymmetrics. And then I have introduced a couple of generalized spin helicity selection rules. But I use that as a way of doing partial wave decomposition. and also incorporating proper version of the unitary equation for electromagnetic asymmetrics, I show that by setting 2 to 2 scattering, its lowest partial wave asymmetrics can be completely determined. And in fact, very non-trivially, in its lowest partial wave, only helicity flip process goes through, and no helicity non-flip process can occur. Okay, with that, thank you. Thank you for your focus. Thanks.
Thank you very much for nice talk. So, question?
Thank you very much for interesting subject and nice talk. And
Thank you. Yep.
I'm a total novice because I'm not even a theorist. But anyway, I have very naive question. Suppose we know in our universe there might be some monopoles and some dions. How would it affect calculating the electric dipole moment of fundamental standard model fermions or magnetic moments with your formalism?
A good question. Let me think. I never thought about it. I'm not so. Let's first talk about easy question first, right? So can S-matrix program ever compute, say, electric dipole moment in theory without, say, monopole first? Okay. So the answer to that question is yes. In fact, there is a on-shell S-matrix way of computing electric dipole moment, but I should say that that's more like there on-shell S-matrix method is used just a way of computing some loop diagrams. Okay, it's basically a technique to compute the loop diagrams using some sort of cutting rules and generalized unitary techniques. Now, good. So therefore, in the pre-Jensen monopole, if we know what kind of diagram to be computed, like for example, I want to have one photon line with 2 electron lines, right? And then the question is, can I compute that 3-point function in the pre-Jensen monopole? I would say in principle possible, because now you can start thinking about like there is a 2 electron coming up, positron coming up, and there is some monopole as an intermediate state, and then maybe it's connected to another fermions, and they eventually lead to the some photon. And you can probably make use of this generalized unitary and generalized cutting rules to compute that. Having said that, I'm not sure if I can learn any new intuitive physics out of it. Maybe it's possible, but I just don't know the answer. But that's a great question.
Yeah, I mean, my original motivation for this question is that in the ordinary particle physics, we approach it perturbatively and build up some intuition like tree diagram, loop diagram, things like that.
Yeah,
and
that's right.
The magnetic moment calculation is also follows in that approach. So how would it change with your formalism? That was my main motivation of the question.
Right. So good. So like I said, so far as I know, the usage of S-matrix program in computing electric dipole moment, it is still very perturbative in usual case. And in our case, if I do have a final state where there is actually a monopole sitting as a part of the external state, then there's extra constraint on the form of the vertex. Okay, that's how I got the mileage out of it. But if the external state consists only of, say, electrons and photons, but without any monopole, then there's no role played by this extra helicity, pairwise helicity factor. There, I'm not sure whether there can be already immediately extra constraint that can determine this electric dipole moment almost non-perturbative. I doubt, but nonetheless, you can ask any corrections. If theory contains monopole, what kind of correction you can expect in the electric dipole? That is conceivable, but I don't see, at least at the moment, that we can just write down the answer for that immediately.
Okay, thank you.
Yeah, thanks.
My understanding is that without monopole, there are some techniques that you can start from the tree level S-matrix and then construct one loop, two loop, etc. from the
So exactly.
That's what Dr. Hong already explained, I think.
Yeah. So good. So yeah, exactly. So yeah, for example, yeah, you can compute one of the very interesting application of the asymmetric method to say loop diagram is what is the asymmetric version of talking about say chiral anomaly. So you can compute three triangle diagram, but using asymmetric techniques. And there, instead of talking about charges and the anomaly, you're talking about locality and the consistent factorization and that kind of language. So there is asymmetric realization of the say chiral anomaly in that language, but nonetheless, it's not like there you just write down the answer like non-perturbatively. You just try to fuse 3.3 diagrams like that. You just try to fuse so that you compute it using what's called the generalized unitary. But nonetheless, it's very intriguing result.
Okay. Any other question?
I have a question.
Yes.
You said there is no crossing symmetry. Symmetry is violated in this formalism.
Mm-hmm.
So there is no any connection between S channel or T channel?
Yeah, great. Good question. So exactly. So let's say originally I'm interested in fermion monopole going to the fermion monopole in this, let me call it S channel. I don't know if you see my fingers or hands, but probably let me go out so that you can see better.
I can see.
Oh, you can see? Good, thanks. Let's say you are interested in this. The statement is that electromagnetic asymmetrics does not have S crossing symmetry. So the statement of crossing symmetry is to say that the form of the asymmetrics for the S channel process, the T channel process, U channel process in usual non-magnetic asymmetrics is the exactly same analytic function of the P. Okay, so it's the analytic function of the complex momenta. And then in order to, for example, read off like cross section in the S channel, you just need to go into the proper part of the complex momenta plane. In order to read off the corresponding cross section in the T channel, you have to go another part of the complex momenta plane, and then it is guaranteed to get the right answer, and so forth. So the then statement about the crossing symmetry violation in the case of electromagnetic asymmetrics is that if you construct asymmetrics, as I told you today, for S channel thing, there is no guarantee that any sensible physics process going on corresponding T channel. In fact, you're not supposed to use that because there is no crossing symmetry. In other words, if you do the crossing transformation, the corresponding process is not even physical process. So you're not supposed to look at that. I don't know if I address your question properly. If not, please ask me again. I'll try again.
No, thank you.
Yeah, thanks.
Okay. Any other question or comment? Okay.
I'm sorry. I have a very naive question.
Yes.
Can you consider a scattering between monopole and fermion with the spin 3/2?
Yeah, in principle, that's possible. So our formalism makes sense for arbitrary spin. Even monopole can be the fermionic monopole. It can have a spin half, okay? And then say some gaugino or gravitino, and then talking to the spin 3/2 monopole with the Q 5/2. In principle, you should be able to write down all of those things. Oh, I should mention, our original motivation for all this work was, there's this famous work by Rubakov and Kalan. And the story there is that if you have a GOT model, like SU5 GOT model or SO10 GOT model, which eventually broke down to the U1 ENM, and therefore GOT model generically does have a monopole solutions, two of the Polyakov monopole solutions. But it turns out that the existence of monopole solution in the GOT model speed up proton decay. So it catalyzes proton decay process. And then people wanted to understand how fast that is. And the conclusion based on field theory work is that it's going to be fast. Okay. But there is some controversial statement too. So, but then no one has successfully computed asymmetrics for that process at all. Okay, they just estimate it may be fast enough, that kind of thing. So we wanted to see if we can actually write down the answer for that. But this is twice version of that work, meaning I just studied 2 to scattering, but for proton catalyzed process, it is like 2 to several process. So it's more involved, but nonetheless, that's definitely our next thing to think about. But going back to your question, yes, our formalism allow you to compute scattering of the fermion with a spin 3/2, with a monopole with arbitrary spin, and with the arbitrary Q. That's right.
Thank you.
Thank you.
Okay. Other question or okay. If not, then let's thank speaker again.